So we're going to look at something that's called Euler's method. Now, basically, Euler's method is a way to computationally find solutions to differential equations. So let's just jump into it. Let's think about something like this. Consider the differential equation dy dx equals f of x. So just to sort of cast your mind back to what a differential equation is, says the derivative of some function is equal to f of x is equal to some other function, right? And we've also got here some initial conditions. We've just got the points on the curve that are on our solution curve, x naught, y naught. So that just looks like this. So let's put the first thing in, which is to say that we've got some solution curve here. We've got y equals capital F of x. Now that shouldn't be too surprising. If you just look at this, if you were to integrate both sides, on the left-hand side, you would get y. On the right-hand side, you would get an antiderivative of lowercase f of x, which we're just going to call capital F of x. That's what we've got here. Now, what we're going to say at the moment is we've got some point here at that we've got some initial coordinates, initial values, so x naught, y naught. So that's at this point here, right? What we're going to do is we're going to put a tangent at that point, and you'll see why in a moment. So we're going to put a tangent there, and then we're going to make a triangle out of it. So we get this triangle situation going on here. So what we can say about that triangle is this distance here is h. So from x naught plus h gets us to this point here. Okay, what we're actually interested in is this point. And the reason we're interested in this point here is because this point here is actually kind of close to our solution. And this is what Euler's method is all about. It helps us find out where points would be close to. So this is a point that's actually on our solution curve, but this point here is not far off. And that's essentially what Euler's method does. It just generates new points that are close to where our solution curve might be. If you've seen the video on slope fields, we're kind of in that sort of similar area. It's sort of giving us an idea or a picture of what the slope field might look like, or I should say what the solution to the differential equation might look like. In any case, if we consider this point here, we can see that the x value of that point will be x naught plus h. The next thing we're interested in is how much has it moved up, right? So what we could say is we can call this distance here k. And then we're going to say the following. Okay, and this is where it gets a bit tricky. If you think about this point here, the differential equation dy dx equals f of x, well, that is the gradient of a tangent line at x naught, right? Because that is f of x here is the gradient of our solution, which is shown in red, right? So f of x naught equals rise over run. Well, k represents the rise, and we know that our run is h. So f of x naught equals k over h. And if we just rearrange that a little bit, we'll get, therefore, that k equals f of x naught multiplied by h, just by multiplying h to both sides. Okay, so what we get for this point here, I think you would agree, I hope, is that the x value is x naught plus h, and the y value is y naught plus f of x naught multiplied by h. Okay, and then so what we do is we just call that our new x1, y1. And so this point here again, is equal to x1, y1 is equal to all this business. Okay, it's just our next step in the process. So we just give it a new name. Okay, it's one of these iterative processes. Okay, so this is what we're just going to put in our table here. Okay, so we're going to say x1 equals x naught plus h, y1 equals y naught plus h times f of x naught. So that's this here. Okay, and then you keep going. x2 equals x1 plus h, because you could just keep going, right? You could keep going along, and you would keep getting values that are sort of close to or approximations of your solution to the differential equation. Anyway, and then we keep going. x3 equals x sub 2 plus h, y sub 3 equals y sub 2 plus h times f of x sub 2. Okay, dot, dot, dot. And then if we did this generally, we'd say, all right, x sub n, for any x sub n, we would say that's the previous x. So x sub n minus 1 plus h. And for y sub n, any y sub n would be the previous y value plus h times f of x sub n minus 1 minus plus h times f of the previous x value. So it's quite a challenging concept. I suppose what I just want to sort of finally wrap up with is just this idea that it's a process, it's an iterative process, and it's not like Newton's method. I'm not sure if you've seen that, but it's not like Newton's method where it just gets better and better. This process can just sort of help us get a feel for what the solution might look like, because some differential equations just can't be solved algebraically. So you need to have some other method. And this is obviously Euler's method. So if we were to go to x2, well, what we'd get is a situation where, maybe x2, we would take a tangent at this point now, right? We'd take a tangent at this point. And so then we would get another value here that would be sort of close to the red line. And then you just keep doing that. And it just sort of gives you an idea of where the points are on the solution curve. Because remember, we don't know anything about this solution curve. This is here just for visual effects. We actually don't know what this actually is, right? It's just there sort of to help us, because you've got to do this all without this diagram when you're solving problems, right? Okay, and then so yeah, maybe x sub 3 is moved along this much. And then, hopefully you get the idea. Some other points, if you just kept doing this process, you put another point, you do x sub 4, that might be there. And then x sub 5 might be there. X sub 6 might be over here. And you start to get a feel for what the solution curve looks like to this differential equation. So challenging idea, but the key thing is you understand that it's just a process to help you find solutions to differential equations that you can't solve algebraically. All right, good luck with all your studies. I'll see you soon.